to be going just fine.
Sheldon, you didn't have to notice. You could have been late or early to all your meetings.
Yeah.
It seems your colloquium has developed fine, right? So it seems to have established as a kind of standard thing that is, well, people notice, it seems. So
we hope so. Seems like a nice way to, to stay connected through ongoing.
So the idea is to keep it in this format when maybe things are getting back to normal, when, say, Corona gets a little better and so on. Or, well, you don't know, probably.
We're taking it a few months at a time.
Yeah, but we've had no discussions about ending it.
Mm-hmm.
I mean, we can't put it into a virtual format because the organizers are scattered all over the world. The participants are scattered all over the world. I mean, it's virtual by design in a way.
Mm-hmm. Oh, I mean, yeah, I guess that's good. And in fact, sort of, I guess there will be a few things remaining of what, well, one was forced into due to Corona. I guess
you can call it a COVID gift.
Yeah.
Maybe time to start, Tudor.
Yeah. So it's time. Let me record, and we're live on YouTube. Yeah. So welcome back, everyone. Today we have Joerg Teschner from Hamburg and Desi, who will tell us about the complex geometry of topological string partition functions. And if you have questions, you may go ahead and unmute yourself during the talk, or just put the questions in the chat, and we'll relay them to Joerg. Thanks.
Yeah. Thanks a lot for the kind invitation. I really appreciate the opportunity to present some recent work here. Let me maybe share and go to the full screen. So, yeah, what I'm going to talk about is going to be based on some work which, well, by now extends over a few years. So here in basically alphabetical order rather than time order. So this was work joined with Murat Alim, Joanna Koman, Pietro Longhi, Eli Pomoni, Apan Saha, and Ivan Tulli. And what I will do, sort of the plan or the overview is, on the one hand, as a kind of introduction, because it's a kind of neat and rather explicit example, I will discuss the topological string partition function for the resolved conifold geometry. This is useful in the sense that it reveals some, but not all, aspects of a picture which is slowly unfolding and which is sort of, well, which I try to summarize by the title, namely to uncover the complex geometry underlying the definition of, or non-perturbative definition of topological string partition functions really as analytic objects. Okay, so this here basically is a kind of motivation slide, which some of you may have seen already, well, slightly modified. So the interest is, of course, manifold, and most of you will know this very well. So there is a lot of interest, both from the point of view of physics, motivated by the desire to study effective supergravity or superstring actions, the relations to supersymmetric partition functions in supersymmetric field theory. But there's also a lot of rich mathematics going with it, because it seems really that these topological string partition functions are a little bit, and that's a kind of recurrent theme perhaps, a kind of what in German is called eierlegende Wollmilchsau, so a kind of mythical beast giving, well, eggs, wool, milk, and meat at the same time. And that seems to be the character of these topological string partition functions. They give us Gromov-Witten invariants, Donaldson-Thomas invariants, and other invariants which have independent and often quite non-trivial mathematical definitions of their own, and they're kind of unified. They're like, well, different sides of one and the same, or different aspects of one of the same object. Various approaches have been put forward to its computation. Yeah, the names of the games: topological recursion, holomorphic anomaly, topological vertex, matrix models, and more. And the goal is to find a geometric characterization of non-perturbatively defined partition functions, which are sort of, which is done in such a way that the BPS spectrum is encoded in a, well, relatively simple way. Okay, so we are going to approach the problem basically by, in some sense, returning to the origins and then, well, presenting an example where one can see, as I said, some aspects, but not all. So the topological string free energy basically has a definition from the worldsheet approach to string theory, which, due to supersymmetry and localization, I'm sure I don't have to tell you all this, reduces to a well-defined, rigorously defined mathematical problem, the problem to compute Gromov-Witten invariants. So the free energy, whose exponential gives us the partition function, is having an expansion in powers of the topological string coupling constant, which is a genus expansion, and it is weighted by the famous Gromov-Witten invariants, which here are in a double expansion in the topological string coupling constant, and then exponentiated complexified Kähler parameters denoted Q beta. Well, a priori, as it is defined, this is just a formal series. So one of the basic questions is whether there do exist analytic functions which have this series as asymptotic expansion, and that's not so clear. And I think, yeah, the results until recently were relatively rare to this effect. And well, it may be, and that is of course a standard theme which we will come to next, it may be that even if there is an analytic function, it is by no means unique. So if this is an asymptotic series which is not convergent, then the typical situation is that there are more than one, say, analytic functions having one and the same asymptotic expansion. And so we have the issue to choose which one is right for us. Okay, so we specialize to the example already mentioned, already advertised. We want to, so here, of course, yes, what we have in the back of our minds is that we're considering a string compactification. So there is a Calabi-Yau 6-dimensional manifold to which we consider then the maps, and it is basically the counting of these maps defining Gromov-Witten invariants. So now we specialize to a very special such manifold, compactification manifold, which is called the resolved conifold. I actually do not want really to go into the details of the geometric description of this manifold, which most of you will know very well, but rather just quote what some basically classical work in physics going back to Kumar-Vafa. In mathematics, important step was taken by Faber and Pantaripande around 2000. So what this gives as a basically explicit form of this series representing the genus expansion of the topological string. And here it is written. We see some multi-logarithms of the exponentiated Kähler parameter, here denoted QF, which, if you're familiar with toric geometry, describes basically the gluing of two such vertices. And there's some Bernoulli numbers, and the rest is, I think, pretty explicit. So it's some very explicit object to study, and that is, of course, yeah, something known for a long time. But apparently what was not known is really sort of the theory of, well, basically all reasonable non-perturbative completions or summations of this series. And this is, well, what with Murat, Arpan, and Ivan, we did relatively recently. The basic idea is, of course, very classical. It is the Borel summation. So it is basically the most classical and standard way to turn divergent series, like, for example, here in a more generic form we're looking at right now here, sum over an lambda to the n, how to turn them into actual analytic functions with certain domains of analyticity. And the key step is to do the Borel transform, I mean, to first build the Borel transform by basically introducing here some very nice damping extra factor, which produces out of a divergent series a convergent one. Hopefully, this of course depends on what coefficients we have and how they grow with k in this series. In our case, I can assert you this works. And then you can plug it into integrals of this type, basically Laplace transforms, which defines a something. And as a matter of fact, and here, well, I'm a little quick, presumably you've known this, you've seen this elsewhere. So if you take A0, you take Laplace transform then of this object, this auxiliary object that is called the Borel transform. We're defining function. And this gives a function for, well, rays we can say have emanating from the origin in the complex plane. And whenever the rays are such that these integrals make sense, and which, well, of course, involves two conditions. There should be convergence at infinity, but also which it can happen and will happen and does happen in our case, that the Borel transform has singularities, so we should not hit the singularities. But whenever this is so, and we will see an example in a moment, the example of our interest, yeah, we have to find something. And it's really elementary exercise by basically Taylor expanding here the integrand, the function g of t, the Borel transform around t equals to 0, and term-wise integration to check that this thing here has the original series as a formal or asymptotic series expansion. The point is, it does have this series for any choice of row, and there may be multiple choices of row. And when I change the choice of row, I may get a different function. So really, I'm having a whole collection. In our example, it will be an infinite collection of such functions, all having the same asymptotic series. And the whole, well, the whole point will be, the fun will be sort of to understand how all these functions are related. And okay, let's maybe look at the example that we're interested in, the resolved conifold topological string partition function. There is already a little bit of work on the Borel resummation for that example. In particular, there was beautiful and important work of Paschietti and Schiappa, who did find already a formula for the Borel transform of our free energy of the topological string. Starting point of our work was an alternative expression, which in some respects turned out to be, yeah, for some aspects of the story a little, well, it was useful for us. It served us a good task and allowed to kind of get a more complete picture of the story. Although, and I will occasionally mention some important results indeed were in the literature before. So yes,
are these formulas for the resolved conifold case only, or for the general case?
This is for the resolved conifold only,
okay,
for sure. So of course, well, you may speculate if maybe by, well, rewriting, for example, the series in Kupakuma-Wafa form, there may be generalizations that can do the job, but that's for the future. it's not yet. So for the moment, it's something very concrete for a very concrete example. And it will, of course, depend heavily on what kind of Calabi-Yau we're considering. All right, so yeah, I said what is important is, of course, the analytic structure of this Borel transform. So because, yeah, we have to see where we can integrate, where can we put our rays. And so what this picture here on the left is supposed to depict is the location of poles in the plane. Actually, I'm not sure. Yes, I did a bad job here with giving names to the variables. So what's the role of t here is going to be placed by the variable psi. Oh dear, this is, and t on the other hand is what corresponds to the Kähler parameter. So I overlooked sort of okay, so psi is now what we want to integrate over to do the Borel transform. That is the variable here. And here are sort of on these dashed lines, we find poles. That is an example for a certain choice of the Kähler parameter t in this expression. So basically, wherever we see wedges here, we can integrate. And so, well, the wedges wk, we label them by some integers and so on. And for each of these wedges, we're defining analytic functions in the wedges. That's what we get. And good, there is a famous Stokes phenomenon, which here in this context is just that when we change the wedge in which we put our ray along which we integrate to do the Borel transform, we're getting a different result, so we can compare. So in some sense, we can say along these lines in the complex psi plane, the Borel transforms exhibit jumps. And it is interesting and turns out to be instructive just to compute them, which we can do from this formula with a little work and so on. We find something which has a characteristic dialog dependence. And furthermore, what's kind of interesting is here the exponent, because yeah, this is going to have an interesting meaning in a moment. So maybe, well, just notice there's some structure here. Furthermore, let us notice that, well, somehow it so turns out when we go along the positive real axis, that's a sort of distinguished object. And with some work, which is a little technical, of course, we can do the integrals and rewrite it in this nice form. And when, well, some of you may recognize it. This is a famous special function, triple sine is the name. Anyway, that's what we get. This is just the result of calculations. This is just, well, technical, but, well, not completely straightforward. Perhaps we were, and I want to emphasize this following the steps of Garoufalidis and Kashav, who had been doing before a similar exercise. Well, exercise is a bit inappropriate, a similar job for the Faddeev's non-compact quantum dialogism. Anyway, so let's now turn to some aspects of the more global picture that we find, and then we gradually turn to the interpretation in terms of, well, what are we going to be after BPS states and their counting. All right, so rho is a variable, right? So this basically is associated to the wedges in which we can put our ray along which we want to integrate. And the observation that is kind of interesting is we may always split it into two pieces. There's one piece which doesn't depend on the ray, and there's another piece which does depend on the ray. And both are kind of known. So we can recognize them as something known, although they had not been sort of found in this precise context, in this form precisely before. So what do we find? So there's this thing which doesn't depend on the ray. That is basically what we get when we reorganize, following Gupta-Kumar-Vafa, these formal series, which was a formal series in powers of lambda, can be reorganized into a series of powers of e to the 2 pi I t. Right, so rather than, I mean, this can be convergent as a series when, for example, t has a positive imaginary value, and it can define as something. That, of course, was well known for a long time. This is, for example, what we would get when we compute the partition function of the resolved conifold via topological vertex. But there's more, and that is the piece here, this FD. D, of course, stands for D-brane, and that is what depends on the ray rho. And if you look at it, you find indeed sort of the characteristic behavior of D-brane effect. So 1 over lambda, exponential of 1 over lambda is the type of behavior. So it depends on the two variables. So it can be written, it can be recast as a function of two variables that we call Q prime, I mean capital Q prime and lowercase q prime, both having this characteristic 1 over lambda dependence. Okay. Furthermore, well, just by computation in our results, we can play with array. We can go from, well, here real axis, where we have this, to imaginary axis. And what do we find? We find on the imaginary axis 0. And when we go to the real axis, we find FNS. NS stands for Nekrasov-Shatatashvili, and okay, there's a long story I cannot quite, well, not at all give justice to, but there is a refined version of the topological string due to Iqbal, Wafa, and somebody, Iqbal, who's, I think there was a third. Anyway, the refined topological string, and this has, well, one more parameter. Not only lambda, but it has two parameters, and you can take a limit with respect to one parameter, giving, which is called the Nekrasov-Shatatashvili limit, in analogy to something that one can do in the gauge theory context. And what it would give here in our example is this specific explicit function, and this is what we find along the real axis. So here the fun is, well, rotating here the wedge in which we do our integration brings us from, well, just the Gopakuma-Vafa only to Gopakuma-Vafa plus FNS. And this sum is also something that had been proposed and considered before. Namely, when you take this sum here, you're getting something that actually has, and that was observed in particular by Hatsuda, Marino, Moriyama, Okuyama. So these were the first observed. This has nicer analytic properties than just this FGV, which has troubles when lambda is on the real axis, obviously. And this sum here has a remarkable sort of pole cancellation phenomenon occurring, and it gives something that, well, basically has meromorphic continuation over the lambda plane. So it is a better analytically behaved object than the pieces themselves. So the point is somehow now that we find all these kinds of ingredients as being parts of the unified picture, which is emerging when you just study in a sort of straightforward way the Borel transformation, the Stokes phenomena, then it basically interpolates between all that had been proposed before. I mean, a general basic question, of course, in well, non-perturbative completions is which one to choose, and one will generically not get around a certain arbitrariness in this. So it's kind of perhaps appealing that the different proposals that have been made before now fit into a unified picture, just as being related by the rotation here of the integration contours we can do, and which is natural to do in this context.
Sorry,
anyway,
just a
yes,
silly
please.
question on that slide. So FD
You want here? Yeah.
Yeah, FD was supposed to be a function of this big Q prime and little q prime that involve like the S-dual variables. But when you wrote down FNS, that still seems to depend on the original ones.
Yeah, true. Oh, okay. Let me see. Do I have a better for? Oh, just see. Maybe no.
So there's no typo there, right?
Okay. There is a typo here. Dear, this is. Well, I mean, good. It escaped my attention more than one times, it seems. So, well, the point is, of course, this is just the traditional way one defines it, where one, with some purpose, uses the variable g, and the variable g wants to be 1 over lambda, or proportional to 1 over lambda, ultimately. And
Wait, and is that also, is t also supposed to be t over lambda?
This here is a typo. Yeah, it's sorry. Also, I mean, in any case, I can assert you that really, yes, when you rewrite it, I mean, there's also a small resummation you need to do. This is not the form which exhibits the fact that here you're getting a function of q prime, well, capital and lowercase q prime in the most obvious way. But in any case, this 1 over lambda, one should see more obviously than you see it here on the slide, which has typos. Yeah, I shall.
Thanks.
Good. Yeah, thanks for pointing this out. This is, of course, annoying and embarrassing. Sorry.
Can I ask one more question about this slide?
Sure.
So, as a mathematician, I often think of D-branes as submanifolds with structure.
Yes.
For this D-brane, for this series that corresponds to D-brane effects, can I think of the D-branes as being localized anywhere, or is it?
The D-branes in question, in fact, okay, that's basically what we turn to on the next slide, are also pretty well known, namely for the BPS states, the set of stable D-branes in the resolved conifold has been understood from different points of view already quite a while ago. So in mathematics, there's Joyce and Song. So they have representations either as coherent sheaves, if you like to represent D-branes as objects in the derived category, or of course there's a mirror description in terms of well, presumably objects in some Fukaya category, which in the physics literature was investigated in the with the help of exponential networks. Romo, Longhi, and Banerjee have been working on this. So these are at least two sources where you can read about the precise mathematical description of the objects representing those. And indeed, it sort of prompts me to stress that, yes, indeed, it would be, I think, nice to clarify sort of from the worldsheet perspective where these contributions come from, which to the best of my knowledge hasn't been really done, in the sense that, yeah, you would like to attribute them to, well, disk amplitudes with boundaries represented by these stable D-branes, and honest worldsheet computation sort of giving these effects. Well, maybe you can point something out that I don't know, but I don't know about such a direct explanation yet.
Well, I don't know either, but that's very helpful. Thank you.
Okay, so yeah, let's continue with a link to the BPS spectrum. So, okay, BPS states, of course, they have a lot of prominence. Maybe I really can. I mean, these are particular states in that are protected by supersymmetry. I really can't introduce into this at all, but I suppose most of you will know this very well. So what are the characteristic data characterizing BPS states? These are on the one hand charges. There's a lattice formed out of the possible values the charges can take. In the particular case here of resolved conifolds, it's a two-dimensional lattice where basically the directions are associated to D0 brane and D2 brane charge, so objects having zero or two-dimensional support. The other characteristic, given things like energy or mass of the branes, are the central charge functions. So here there's a very simple such dependence of the central charge functions on the Kähler modulus T. And well, the dependence furthermore on the charges is also very simple. Well, okay, this is always going to be relatively simple, but what is of course interesting, I mean, what is peculiar here is the simple dependence on the Kähler parameter. And yeah, and then, however, of course, there do not have to exist such states for arbitrary charges, and that is the very intricate and interesting problem of BPS state stability or D-brane stability. So sort of the key objects of interest are the so-called BPS indices, which roughly speaking tell us whether for a given charge there can exist one or multiple, well, it's an index, it's a weighted sum, but whether there can exist such BPS states or not. And here are the BPS indices that, well, as I said, have been determined in terms of coherent sheaves by Joyce and Song, or in terms of exponential networks by Banerjee, Longhi, and Romo. So these are known values. And what we can now observe is that there's a rather nice and intriguing one-to-one correspondence between the Stokes jumps, namely the pattern of rays that we see here, on the one hand, and second, the analytic form of the jumps, on the other hand, for the Borel resummed partition functions of the resolved conifold. Namely, one can quite uniformly write the jumps, including, and that's a slightly sort of tricky aspect of the story, including the imaginary axis. One can rewrite it in this form. And what you can recognize there is that basically there's a multiplicity here in front, which is given by the BPS index. And second, you can write it, in fact, as a function of the central charge function associated to these D-branes over lambda again. And then, okay, one is taking here peculiar, well, combination or derivative of the Li2, which is kind of a standard building block function appearing here in this context of exponential of central charge function. So basically, it's completely, I mean, once you're told which functions to use, basically the data that are free in the description of the jumps are the BPS state data. Okay, and furthermore, if you look at sort of these jumping or changing non-perturbative contribution to the full answer, the one here, well, if you just ask what it is for a specific ray, you will find it is just whatever has positive imaginary part of Z gamma, which basically means it is composed out of exponentials, which are nicely exponentially suppressed for a given phase of lambda. So you're basically summing over all stable D-brane contributions, giving exponentially suppressed contribution, non-perturbative contributions. So this kind of seems to make sense. But as I said, I would like to know a more specific, I mean, a more detailed, say, direct explanation of this, which is not going via Borel summation, but which sort of gets it directly from the worldsheet. Anyway, so that is sort of the first half of my talk. I would now sort of turn to, well, a more general picture, which I want to outline here, which will be more descriptive, but maybe it's a good time to ask for questions and also ask the chairman for the timing, that I can see how much of time I've left for the rest.
So you're about halfway through the time, a little more than half.
Sounds good.
And question, so in the Donaldson-Thomas partition function, depending on chamber, there are also jumps that look sort of similar, except they don't involve this exponential of something over lambda. The jumps there are proportional to lambda. Do you understand the relation?
Yeah, that's going to be part, although perhaps a somewhat implicit part of the second half. What I, in view of time, chose to skip in this talk is that this is only half of the coin. We have basically here described the results for the weak coupling expansion. But as it turns out, and that I think was very much intriguing us and sort of exciting us in a way, the same function here that we found as a non-perturbative answer also has a strong coupling expansion. And if you look at the strong coupling expansion, it has also Stokes phenomena, and it jumps, and it has chambers, and so on. And in the strong coupling expansion, what you find is something that was known for a long time, namely it's exactly the the jumping behavior of the Donaldson-Thomas partition function for resolved conifold as studied by Jafferis and Moore. So it's basically, in a sense, it makes sense, right? So at strong coupling, you have supergravity, and there you find sort of this type of what is, I think, in a sense, yeah, less obvious is sort of that we have a similar pattern, but with other functions and other jumps at weak coupling, in particular with the Li2s, which we wouldn't have at strong coupling and so on. So I will say a little bit about this in the second half, although I will not probably have the time for a fully like explicit and full coverage of all this. I mean, it's a very, I think, intriguing and interesting aspect of the story.
Thanks. Are there any other questions?
Yeah.
Thanks.
Okay, so I want to outline, I want to take the opportunity, I want to dare, because it's, I think, now readily taking shape, to present a very rough sketch of the emerging, more general picture. And my or our personal understanding of this draws from many sources. Well, what I knew best and what was sort of, at least for my very personal understanding, most important is assembled here in a kind of in a kind of overview form. So there's quantum mirror symmetry, integrability, quantum curves, going back to this beautiful work of Gennady Dijkgraaf, Clem, Marino, Bafa, and others, which then developed a bit over the years. I mentioned already important, beautiful work on non-perturbative definitions of topological string partition functions by Marcos Marino and with various collaborators, which was also related to the idea of quantum curves. That's an aspect which I can't touch today, a different talk maybe. On the other hand, geometry is going to be sort of a leitmotif, a kind of main theme in what I'm going to try to propose. And as a matter of fact, looking at it from a rather different perspectives in the works of, say, well, with Joanna and Pietro and Ellie, we ultimately discovered that some aspects already had appeared in the work of Alexandrov, Persson, and Pioline, and so on geometry of hypermultiplet moduli spaces. In fact, related proposals have already been made at that time. But a lot was also strongly motivated by more recent work of Tom Bridgeland, who was thinking about sort of a general program to associate to the these data describing BPS states, the space, well, a space of stability conditions, and then introduce natural geometry on this space, natural geometric structures. And in fact, well, he had proposals and results relating this also to topological string partition functions. And yeah, this is sort of here our take on the subject. I mention here some works which are kind of historical in the background, which did not consider topological string basically at all, but nevertheless they were in the context of, say, well, AGT, gauge theory, relation to CFT and integrable models, very important, and actually inspired a lot our approach here, which we were developing, well, I mean, since a little bit now. So work of Gamayoun, Joerg of Lissovy, and well, then at some point, in order to understand the conjecture that they had made, well, I entered a little bit this game, and it's about, well, I mean, this is about tau function as a sort of main player, and we will see some kind of tau function very soon. Anyway, this is just sort of to do, well, the meager try to do justice to well, literature, sources of inspiration, and other people's work. Although It is incomplete for sure. For example, exact WKB is an important aspect of the story, which simply here I cannot mention. Anyway, so when you are starting to think about geometric description of these partition functions, then sort of basic question to ask are which function and which space should they live on? So what could be, for example, when the arguments here, I mean, if you want to consider this here as functions on some space, then the arguments of these functions, the topological string or variants thereof, should probably be coordinates on some space. And this sort of brings us slowly into the direction we want to go. So what Tudor had been already asking about were sort of the objects which have been studied a lot, namely as counting functions. So the DT partition functions, counting functions in particular of bound states of D0, D2, and D6 branes in a non-compact situation where you have a single D6 brane and you're considering whatever you can bind to it. So this is, well, for local or toric Calabi-Yau, something that has been studied very extensively. So then you find just, you form just generating functions out of the BPS indices, again, some indices whose precise math definition I will skip. And you're defining them, they're supposedly counting what the physicists like to call BPS indices, and you're forming a generating function out of that, where you use a variable u, going to be related to topological string coupling soon, and scalar parameters here as sort of the formal variables you use to build a generating function. And these objects are locally constant, but change across walls of marginal stability. That is this wall crossing and jumping story that, for example, well, people like Jaffiers and Moore, and then many others have studied a lot. There's furthermore a famous result by Maulik, Nekrasov, Ukunkov, Pantaripande relating this object to the topological string partition function, as already discussed before, but now in a somewhat larger generality. So we now can replace in our mind the resolved conifold by maybe, for example, other toric Calabi-Yau. However, one of the points that is not completely new, but very important for this story I want to make is that, yeah, it in the end turns out to be better to consider what is called sometimes the dual partition function, which is counting D0, D2, D4, D6. So now we can also have, so here we're summing over basically charges of D2s. Now we have an additional summation over charges of D4s. We have then some chemical potentials we call here eta for the D4s, but otherwise it's a very analogous object. And in this context, it so turns out that actually these two counting problems are very closely related, as has been explained in particular by Dijkstra, Volland, Tsiolkovsky, and Vafa. So basically, we can compute these guys from these guys. That has to do with a description of D4s in terms of fluxes on the D6, which you can basically reduce then, or you can describe this in terms of some bound states of D0, D2, D6. What this leads to, as these authors have pointed out, is in fact a description of this object when you go to this chamber C infinity, which is also called the infinite volume chamber. Then you can actually, thanks to, well, the definitions plus relation D0, D2, D6 to D4 to D0, D2, D6 that these people have discussed, plus Maulik, Nekrasov, Ukunkov, Pantaripande correspondence, to get a relation between this function here and Z top. And it has a remarkable form, namely it's a kind of generalized theta series here, where you replace this Gaussian factor by Z top. And that will be, well, coming back. Okay, so now we want to now, on the other hand, relate it to the geometry of spaces of stability conditions. And to avoid confusion, let us distinguish here this business of what is called framed BPS state counting in the presence of a non-compact brane to what we now turn to, what is, well, the stable D-branes, or compact D-branes that in particular Tom Bridgeland's story is all about. This is the unframed BPS states, so those associated, say, to really compact objects. Okay, so more generally, when we describe BPS states, we have charge lattices which vary, which can vary, well, as a local system over the space of stability conditions. The space of stability conditions, okay, is something that has abstract mathematical description, but which also we expect to be related to spaces of scalar structures or complex structures, depending whether we're in type A or type B in string theory. What we assume is that there's an atlas of local charts on the space of stability conditions where we have basically a polarization for the charge lattice. So we have a kind of taboo, well, taboo basis for the charge lattice where the intersection pairing, which is some object we need to have on the charge lattice, is just, well, kind of off diagonal or symplectic, I mean, of this form. And secondly, then associated to such a atlas, we're going to have distinguished coordinates or a distinguished choice of the central charge functions describing central charges of the corresponding D-branes. So here, just for notations, this is the notations we're going to use. So there's sort of electric central charge functions, and the checks are sort of the what one calls the magnetic central charge functions. Then one doubles the space. That is sort of what Tom instructs us to do. So here we're considering the tangent space of the space of stability. We're introducing coordinates. They have sort of the same kind of pattern. We have electric and magnetic guys and an obvious correspondence with these guys here. So for the case of the conifold, well, we would be then also having to extend the original charge lattice by additional directions, which in fact would correspond to non-compact gains, that non-compact branes, sorry, which we have to introduce here in order to have a non-degenerate intersection pairing. That is a peculiarity of this non-compact case of a Calabi-Yau, that in order, so basically it is the extension of this picture that you have to do when you're working in a non-compact situation as the resolved conifold. But let me not go into this very much, just maybe, well, for reference and comparison, one may note that one sees again here, for example, a direction gamma 0 in these notations would correspond to the D0 brane, then the gamma 1 corresponds to a D2, and then we kind of artificially add here well, directions corresponding to non-compact D4 or D6 branes. In other situations, of course, yeah, there can be also compact D4 branes, and that is then what makes, for example, a thing like this here interesting. Anyway, that is sort of the setup for Tom Bridgeland's well, definitions of geometry on spaces of stability conditions, which works through a type of Riemann-Hilbert problem. I shall refer to it as BPS Riemann-Hilbert problem. The way it works is we are taking the space M, which was here to begin with just the tangent space of our space of stability conditions. So stability conditions doubled. We add a C star. That's like twister directions in a way that can be made precise, but I won't try to do so. And then the point is to basically define a family with a parameter zeta, which is a coordinate on this C star, of deformed complex structures by some atlas, where we have local charts. Well, that's the notations we're using, UI, I, and some index set. And for each chart, we require to have taboo coordinates, which basically bring the symplectic form we want to define, or we are defining here, to the standard form. And the most interesting geometric structure is basically the complex structure, which we define basically in the usual way by describing transition functions among charts, which have, however, a very peculiar and simple form. Basically, it is something like, in other contexts, called cluster mutations. So these are like cluster verbals, and the transition functions are basically represented as cluster mutations. Here are sort of the notations. Maybe for reasons of time, I don't walk through this. So we're having coordinates labeled by charge lattice vectors gamma. We're using here these say Dabu charts in order to produce coordinates on them. So we have then integers labeling these vectors, and this is what we can then use to write these capital X functions, which are exponentials of the lowercase x functions, explicitly in terms of p's and lowercase x's, etc., etc. So these are sort of, it doesn't really matter so much. So this is one piece of, or one key axiom, one key requirement specifying sort of transition functions among charts in our definition of a new zeta-deformed complex structure on the stability space. The second bit is about asymptotic behavior. So when zeta goes to 0, the leading bit are the central charge functions. The next to leading bit are these tangent vector, or the tangent coordinates, tangent space coordinates that were introduced. That's sort of the pattern. And I have to be very quick here, but in the end of the day, it turns out this defines a Riemann-Hilbert problem. And in good cases, one can, when adding some extra requirement about behavior for zeta to infinity, prove uniqueness of a solution on the one hand, which Tom Bridgeland has done under certain assumptions. And even better, sometimes can even prove existence, but that is sort of typically the hard part. One way to approach existence would be via, say, GMN, Gayotto-Murnitsky type integral equations. But anyway, let's not go into this. So the upshot, let me summarize. I have to be schematic in various ways. What are we, the game we're doing here is to start with a complex structure on the stability space, which we call B for base, plus BPS data. These are these BPS indices. These are the main players. This is what either we want to use to define geometry, or we want to use geometry to extract these indices as sort of interesting information. What this defines through this, say, approach of Riemann-Hilbert type problems, like formulated here, are families of complex structures with also Poisson structure coming with it on this space, a kind of twistor space. Here's an important remark I should make, because I think there still is a certain degree of confusion about this. Here's a proposal how this confusion can be resolved. Namely, it has been observed for a long time that the stability space of Tom Bridgeland is, in a sense, bigger than string theorists would expect. Basic reason is basically that in at least original versions, Z and Z check are considered as independent complex coordinates. String theory, what we want to do, I claim, but well, that's probably not my claim, is to impose basically special geometry, namely that sort of the ZI checks, the magnetic central charge functions are related to the electric ones through a prepotential, and that of course chart by chart in this cover of our space. You can view this as basically cutting out in this bigger space, which we have considered here, a complex Lagrangian. So this is a set of equation cutting out a complex Lagrangian, and you can supplement Bridgeland's Riemann-Hilbert problem by this extra condition. What is then non-trivial in general is that it still has a solution. However, well, we can just call the data. So we have two types of data here, the prepotential describing special geometry and the BPS data, which we feed into the Riemann-Hilbert problem by using it to define, like here, the transition functions. We call them computable if this combined problem has a solution, which, well, ultimately is imposing a relationship or describing a relationship between the special geometry and the BPS spectrum. But of course, for physicists, that's not going to be a surprise that such relations will exist. In any case, for this mathematical formalism, I think it's an important step sort of to go from the kind of complex, larger stability space that you can abstractly define from, well, BPS structures and so on, to the space of actual interest in the context of string theory. Furthermore, we expect in the case of string theory ultimately that this smaller space in which you have imposed special geometry relations that then ultimately should be related to a hypermultiplet moduli space in the conformal limit. Okay. Here, in some sense, this perhaps is the slide containing one of the main messages, namely, what I want to claim is that associated to this setup, there are natural sort of generating objects which are holomorphic sections of a canonical line bundle on this twister-like space we have defined through Bridgeland's RiemannHilbert problems. So that basically whenever we have a solution to Bridgeland's RiemannHilbert problem, it will define also a collection of locally defined functions t, which is here, well, a function of our Dabou coordinates, which then, well, just by renaming essentially in the end of the day, this twister variable zeta into lambda. So there's a little bit to be said about this, but in the end, sort of that's the moral of the story. So then these are functions here on our twister space, locally defined chart by chart, which transform as sections of a line bundle for each fixed value of lambda, also known as psi. But that these are the guys that basically define us topological string partition function by expansions of this form. And we've seen expansions of this form before, namely in the relation between the dual partition functions counting d0, d2, d4 to the Donaldson-Thomas partition functions counting d0, d2, d6. So it's I claim this is specializing to the relation we've seen before among dual partition functions and the actual topological string partition functions. It's more general because, okay, here basically the claim, the idea is we have such a thing for each chart. And well, for example, the previous relation was known to hold in a particular chart the infinite volume chamber associated to the infinite volume chamber. Furthermore, how are these the transition functions defining this holomorphic line bundle for which the t's are special holomorphic sections? How are the transition functions defined? Well, they're basically defined canonically in terms of these changes of Dabou coordinates. So just what is sort of the key ingredient in the definition of Bridgeland's RiemannHilbert problem. So the claim is that the transition functions for the line bundle of which these are the sections are just generating functions for the changes of Dabou coordinates. So basically objects canonically defined by the RiemannHilbert problem here a la Bridgeland itself. All right. So yeah, the kind of philosophical message is, I mean, and these jumps, of course, as in the case of the conifold, where we had observed it sort of experimentally, there were the weak coupling jumps, the Stokes jumps, in which the BPS spectrum miraculously turned out to be encoded. So this here is sort of the proposal for the general picture, namely that this is encoded in these generating functions, right? The advantage simply is, well, we're having functions here, and in their jumps, of course, the same BPS indices omega will basically appear, well, as a power, as a multiplicity. But now it's really just a line bundle. What can be more simple than sort of the transitions of a line bundle? And these are what these guys here represent. So, and in some sense, this formula here explains, and well, this formula with the knowledge that we're talking here about local sections of a holomorphic line bundle explains why perhaps these are the much better objects to encode our BPS spectrum in than the actual topological string partition functions. Because if these here transform as sections of a line bundle, well, we can just figure out how these guys transform by inverting this relationship. It's some math, it's some computation, it's some thing you can do. At the end of the day, what you will find is that when these here just transform multiplicatively as sections of a line bundle, it induces a rather complicated transition among charts for the zi's, which are, after all, then going to be related to topological string partition functions. Namely, what we'll find are integral transformations with some non-trivial kernels like that. So I just wrote a rather generic form, because in general, these kernels will be complicated. And that, of course, well, I mean, all this, on the other hand, represents changes of Darboux coordinates. So now here on this side of the correspondence, we're finding objects transforming under integral transformations. Well, this, of course, very much suggests, and I can assert you that this is the correct way to think about it, that here on this side, we're in quantum theory, whereas here, basically, we're classical. It's a kind of classical quantum correspondence here of a sort. And what this, of course, relates to are all these old ideas about topological string non-perturbatively being related to the quantization of the moduli space of complex structures. I think through basically what I'm telling you here, it's becoming concrete, really, for the first time. Well, no, I mean, there have been other works which made it concrete in, well, some contexts and so on. But I think here, this is really sort of bringing us to the heart of the matter, I believe. Anyway, how much time is left? I think I'm sort of...
We're sort of out of time.
Okay. I mean, I have 2 slides which I can really just browse because in some sense they're really more for the experts and I can only... So I want to make very quick comments on relation to hypermultiplet moduli spaces and S-duality, particularly the work of Alexandrov, Pioline et al. So, well, they have set up a
that sounds fine. Thanks.
Is that okay? So
yeah.
Like 5 minutes or so?
Sure.
Okay, then yes, I can at least make a few remarks just to indicate perhaps some interesting directions. Good. So in the description of the geometry of the quaternion Kähler matrix describing hypermultiplet moduli spaces in string theory, Alexandrov, Pioline, and their collaborators have used the formalism which you, if you want, can recast in a similar way as Bridgeland did, with some differences. Anyway, in this formalism, there appears, in order to really get from basically, well, hyperkähler to quaternion Kähler, you need ultimately some extra additional coordinate that they call alpha, which we need for a twistorial description of these geometries. And what they had conjectured, and which sort of comes back on us here, which sort of is now going to be suggested or is suggested from a different perspective, is that indeed these dual partition functions, which became our tau functions, are actually related to the coordinate alpha. Well, of course, locally chart by chart again, in the conformal limit, right? So there is here a metric problem, of course, in the true full quaternion Kähler geometry story and so on. On the other hand, in our story, we're holomorphic. It's a purely holomorphic story. There's something you have to do to relate them, and that is an analog of what was called conformal limit in the hyperkähler context by Gaiotto. And well, in more recent work of Alexandrov and Pioline, a variant of this was proposed or defined in this quaternion Kähler context. And one of the interesting things is that they have a very neat description of S-duality action. And well, on the one hand, sort of, I mentioned already that in the strong coupling summation of the resolved conifold, we basically could, well, discovered, I mean, we could read off basically their proposed realization of S-duality as a operation acting on the coordinates. So it would act something like this. X0 here will correspond to the topological string coupling, which is getting inverted, and so on and so forth. And one of the most interesting things is the relation that they have proposed between these extra coordinate alpha, which we want to relate to the tau functions, and another distinguished coordinate, which is the magnetic coordinate associated to the D0 brane direction. So these are exchanged by S-duality according to Alexandrov and Pioline. So taken together, basically, these three objects are related to each other, are essentially up to, well, some minor points, which I'm skipping, basically the same objects. But now we're starting to see how what we have observed in the resolved conifold by explicit calculation is part of a bigger picture, because what this bigger picture suggests is indeed that we have two types of jumps. One is at strong coupling, where it is just the jumping of these, oh, there should be a check here. The check is, of course, very important, missing the, yeah, it's the X0I check. So this jumping here is the one from supergravity, Jafferis-Moore, and so on. So that is what how this thing here behaves. This here, the alpha has the weak coupling jumps. You have generating functions there of changes of Darboux coordinates. A different functional form, jumps at different locations, and so on. But all this now appears to be glued together to a consistent picture. So, well, the claim here is, and there are partial results in this direction. There's evidence from examples that weak coupling jumps of alpha and the tau functions coincide. And on the other hand, there's a very general argument one can find just on basis of wall crossing formula that the strong coupling jumps, again, the check is missing. So I maybe need to do corrections on these slides. Sorry, of these two guys coincide. Good, and here, maybe this really just in 30 seconds, there's also a nice relation to these non-perturbative completions and the fact that we have, well, the work of Marino and collaborators. So we saw, we expect that this pattern that we observe for the resolved conifold. I see there's a question. Maybe I should first take the question then.
Sure.
Yeah.
Do you want to unmute yourself?
Was that my question? I'm not sure which.
Yeah, that was your question.
I can hear you.
Oh, well, suddenly the word tau function appeared. You mentioned it earlier on, and then you said that these dual partition functions are tau functions. So, I mean, what kind of tau functions are these tau? Is there some associated differential system, something like an isomonodromic system, for which these
there
are
is,
tau functions?
yes. So there are, in particular examples, you recover things that you know very well. So there is a class of local Calabi-Yaus called, well, I sometimes call them class sigma, which is basically the one where the intermediate Jacobian is known to be related to Hitchin systems. In that case, these are going to be isomonodromic tau functions, possibly for higher genus problems. You can do toric Calabi-Yaus, like, for example, F0 Hirzebruch surface, where you will find Q-deformed, so the Q tau functions associated to Q Painlevé. So all this appears in this context, and this is why I call them tau functions, because in examples they reduce to known tau functions that have been studied before.
Thank you.
Good. Yes, I'm afraid I'm really out of time now. So I just wanted to stress or remark there is here, I believe, a generalization of this pole cancellation mechanism, which basically exhibits these two objects, the DT and the CNS, the Nekrasov-Shattashvili part, as sort of being related to the two sides of the coin, right? So it's again related to this here. We have here the DT, the strong coupling side, and so on, and we have the weak coupling side, which have a somewhat different behavior, and that they're put together in certain chambers in a form which produces something with very nice analytic properties is basically a consequence of these Hatsuda, Marino, Moriyama, Okuyama pole cancellation mechanism. Remark about sort of the comparison between these approaches. They had stressed that when there is a definition which gives entire functions, which was proposed as a kind of virtue, because then you don't see all these jumping and transition functions. So you can view it as a background independent representation for the quantum theory describing topological string theory. But I think we would prefer to keep the background dependence, because I think what we start understanding is that this background dependence encodes the spectrum of BPS states through the changes of Darboux coordinates in a nice way. All right, so that's maybe the conclusion slide. I just flash, and yeah, what do I want to stress as final last words? So, well, that non-perturbative effects are encoded in the perturbative expansion by resurgence. I stress this duality, sort of the incarnation of S-duality in this context between weak coupling Stokes jumps, strong coupling Stokes jumps. One thing, maybe the very last thing I want to stress is that it suffices basically to start on one side, right? Because in some sense, even the original formal series we started from, which was defined by Gromov-Witten invariants, defines everything. Everything was obtained just by resummation and repackaging. So it's just sort of how to repackage it, and whether we expand then at strong coupling or weak coupling, which makes us see this or another aspect of the story. This is sort of, I think, the beauty of this unfolding picture. Yeah, you can start it basically from whatever side you like, and then there is a kind of framework repackaging it into information that you may be interested in. All right, so now I should really stop. Thanks for your attention and patience.
Thanks very much for that extremely interesting talk. Are there any questions from the audience?
Yeah, I have rather mathematical comment, if you don't mind. Yeah, it's a mathematical structure underlying this resurgence and maybe some other interesting properties. So in general, if you go beyond this resolved conifold and other simple examples, you might have BPS spectrum which is everywhere dense.
Aha, yes.
All right. And there is an appropriate mathematical structure which we introduced with Maxim. I think it's we submitted to the archive 2 years ago in 2020. It's called analytical crossing structure. And you know, like roughly speaking, you have this charge lattice and the collection of Donaldson-Thomas invariants, but sometimes you can have even a little bit more complicated things. But out of these, you construct, solving this Riemann-Hilbert problem, some analytic object. So it's better to think of this analytic object as a more fundamental. So basically, if we have what we call the analytic crossing structure, we can construct over the complex line. I think the parameter, the coordinate should be a twistor parameter in your coordinate, in your notation. We can construct a fiber bundle with a fiber which is a torus, character torus of this charge lattice. So you don't have to double. And we have a conjecture which has been confirmed in many examples that sections of this fiber bundle are resurgent. So which means that kind of without having much more than your DT-invariants and without solving the Riemann-Hilbert problem, I would rather invert the logic. Your Riemann-Hilbert problem, it's a way to trivialize this fiber bundle over over the sectors, for example, bound by Stokes rays, something like that. But there is kind of a general reason for to expect the resurgence, Borel resummation, in case if you have this analytical crossing structure. So I believe it's relevant. It can it covers also the case when the BPS spectrum is everywhere dense, because you don't have to care which rays are Stokes. You just write the collection of rays, decompose the plane into the union of sectors, and then you glue something over those sectors. And the boundary rays for sectors can be general. They don't have to be Stokes rays. You don't have to care about jumps. So it's kind of a little bit more uniform picture. So, and I believe that the Bridgeland story corresponds only to the case when, I mean, this everywhere dense BPS spectrum is ruled out. So there is, I believe, some problems with his formalism in that case. So this is just a mathematical comment.
No, I mean, yes, thanks very much. This is very interesting. In fact, of course, you know, we were approaching this from, in some sense, from your point of view, relatively simple examples where indeed the worst in the examples that I know a little bit that occurred are accumulation arrays, which play a very interesting and important role. But of course, for the dreams concerning a generalization of this story, where I think there is hope that it has a lot of generalizations, these directions that you're pointing out will be extremely important, in particular, sooner or later, these everywhere dense systems of rays. Yeah, I mean, at the moment, I would have little to say about these cases, but on the other hand, indeed, the hope, I mean, things that also I would like to learn from you at some point, for example, the appearance of these cluster-like coordinates in many contexts, including mirror symmetry and so on, seems very intriguing and a hint of towards a much more general story, which uses similar ingredients, but of course, in many cases, suitably generalized.
Yeah, in your story, you have also on the charged lattice, you have a skew symmetric form. Yeah, which you can make symplectic if you double the charged lattice, which you did. But in fact, the formalism can be developed even without the assumption that you have the skew symmetric form. If you do, you have cluster transformations. In general, it can be not necessarily cluster transformations, but they are quite explicit in terms of this, what replaces your DT-invariants is BPS.
Yeah, of course. I mean, I just didn't have the time to mention there is, of course, some relatively near generalizations that I understand reasonably well. That, for example, yes, there can be degeneracies, but in that case, cluster verbals or cluster algebras with coefficients will make a role to, well, to take care of something in physics called flavor charges and so on. So that is relatively easy to, yeah, to say insert into this this formalism. But yeah, I mean, what indeed for me looked somewhat scary is, for example, everywhere dense systems of rays or something.
So you shouldn't be scary anymore.
Yeah. Okay.
Yeah. Okay.
You know, it would be nice, actually. Yes. Also, other things you mentioned. Well.
Sorry, we had
yeah, please.
We had a quick, simple question in the chat that I just want to pull out because it may have a quick answer. So someone asked, in the classical quantum correspondence relation, in what limit does the quantum description yield the classical one?
Yeah, that would indeed be well, classical limit. That is, in this game, basically h bar is well, essentially identified with the string coupling constant that was called lambda in the talk.
Thanks. And let me just check if there's anything else, because we should sort of end the formal the formal part of the colloquium, and then we can discuss. Were there any other thoughts or questions? Okay, well, let's all thank Joerg again.
Okay, thank you for.
And yeah, thank you very much. And I'll turn off the YouTube recording, and I'll turn off this.
Thank you, Joerg.